So now let's look at the simplest kinetic model. The simplest kinetic model that describes the extent of conversion under, read to yourself, very low conversion condition. Which means when the reaction of its transformation just happened, how can we describe the extent of conversion with respect to time? That is what we call kinetics. Relates the extent of conversion with reaction time of its transformation time. Let's look at it. So let's say the large circle represent the initial material and the white portion represent so-called untransformed part within the material. And the small circles or spheres actually represent nuclei, and the small nuclei we put that in blue represent the different phase, let's say the precipitate phase. And some of the nuclei would grow larger into larger spheres and we call them transformed volume. Okay? And to get this mathematical model to describe how fast that transformation happen with respect to time, we have to make certain assumptions. The first one, as we said, these types of nucleus, for simplicity, let's assume they are all spheres or spherical beta nuclei. Okay, makes sense? That's the simplest one that we can describe. And then let's, for simplicity, assume the nucleation rate is constant value of n. Okay, nucleation rate means per unit time, per unit volume of untransformed volume, how many new small nucleus form. Okay, it has the unit of number per unit time per unit volume. And then for simplicity, let's also assume the linear growth rate of the nucleus radius. Essentially, d radius over dt is constant of v. Let's assume the radius grows linearly with respect to time after it is formed. With those assumptions, and also assuming very low conversion with negligible overlapping, so we do not consider the case when one nuclear and another existing nuclear bump into each other or have overlap. Let's, for simplicity, neglect it. This is very true when for so-called very low conversion condition. When the extent of reaction just happened, when the time t is very, very short. Okay? With these assumptions, then let's say at time t, the volume of single beta precipitate, a single beta precipitate nucleated or formed at time tau would be this one. Okay, we said the volume, okay, of a single beta precipitate. What shape is a precipitate? What shape are these precipitate? We said they are sphere, so that naturally the volume would be 4 over 3 pi radius to the power of 3. Okay, and then what is radius? Radius, we remember we said the radius is growing at a constant rate of v. But then the nuclei may form random form. It may not form at time 0. It may form at time tau, and tau is greater than 0, but smaller than time t. Okay, this is very, very important. We are considering at time t the volume of a precipitate. That spherical precipitate forms at time of tau. It's formed not at the very beginning, not at t equals 0, but at tau, but tau is smaller than t. If tau equals to t, we assume the initial radius is essentially 0. But tau, if tau is smaller than t, then at time t, the total time for it left to grow is t minus tau. Okay, v times t minus tau gives it the radius. Of course, we are assuming the initial nucleus size is negligible. It starts from 0 radius, which is another assumption or approximation. So this equation gives us the volume for a single spherical beta precipitate that formed at a time tau, and then when at time t, which is longer than tau, let's check what's the total volume. Okay, and then the number, let's consider that's for one nucleus, what's the volume, and then let's consider what's the number of nucleus that are formed. The number of beta precipitated nucleated in a small time period of d tau, d tau means a incremental time, but d tau is from tau to tau plus d tau. Tau is a time point, and the tau plus d tau is another time point, which is slightly later than tau. How much later? D tau. Okay, d tau is our small incremental time. Okay, and the number of such spherical beta precipitate formed in that small incremental time of d tau per unit volume would be, we call it dn. dn equals n, which is our so-called constant nucleation rate times time. And of course, we say per unit volume, so we can times 1, which is the same value. So this equation, dn, tells us the incremental or the number of new beta precipitates created in the small incremental time of d tau, and that d tau is from tau to tau plus d tau. Okay, this equation gives us the number of new nucleus formed. With these two, now we can calculate the total volume of transformed beta precipitate per unit volume of the matrix at time t. Now at the time so-called t, which is of course, as we said, longer than at time t. The total volume would be a integration of the volume for each of the precipitate times how many of the spherical precipitate that are formed. Okay, and then we do this integration from with respect to d tau. From here to here, we replaced the v tau with pi over 3 times 4 vt minus tau to the power of 3. And then we replace dn with capital N times d tau. Okay, so that's from the first to the second. Again, the total volume of what? The volume of the blue precipitates would be, integration means summation. Summation of what? Summation of each of the precipitate. It has this volume, and how many of the precipitate, that's dn, and then we have to do this integration when the nucleus formed from time 0 all the way to close to time t. That's this one. And then, of course, for this integration, you put 4 over 3 in outside of the integration symbol. Pi, of course, take it out. N, let's assume, is constant nucleation rate. N can also be taken out. And we said constant growth rate, velocity, can also be taken out. So the total volume of the beta precipitate at time t per unit matrix volume would be 4 over 3 pi n v to the power of 3 times a integration term. Okay, again, n is so-called constant nucleation rate per unit volume per unit time. How many new nucleus, spherical nucleus form? V is the so-called linear growth rate of the nucleus. Pay attention, radius. We are assuming that each of the nucleus is a sphere, and the linear growth rate of the radius, dr over dt, is this v, and we said is a constant. So we put this outside, and then we are left with a integration term of from 0 to t minus tau to the power of 3 d tau. Okay, this is what we have. The total volume at time t for all those spherical precipitate that formed from time 0 to time t. Remember, the nucleation is random. The nucleation happens throughout from time 0 to t. And each of the nucleus formed at a tau, it grows to certain size, which is determined by the t minus tau to the power of 3. Okay? And if we do integration, very simple. It's a fixed integration. We are going to get this one. 1 over 3 pi, of course, constant. N is constant. V to the power of 3 is constant. But this term, integration term, becomes t to the power of 4 from 0 to t if we do this integration. Okay? So this equation tells us the total volume of the precipitate. And then if our starting matrix phase has unit volume, then the fraction of transformation, or so-called extent of conversion, will be, I wrote it here, F. If that fraction of conversion, I call it F, will be the total volume of new precipitate divided by 1 for the unit volume of the starting matrix phase. Of course, Vt over 1 is just the same, which is 1 over 3 pi n V3t to the power of 4. Again, n is nucleation rate. We said it's random, but it's a constant nucleation rate. V is the linear growth rate of the nucleus precipitated radius, and the t would be the time t. Okay, and of course from this equation you see that the volume fraction would be higher if the time is longer, which makes sense. If the V growth rate would be faster, also makes sense. And also F would be the fraction of conversion would be higher if N nucleation rate would be higher. And that makes total sense when you consider it. Okay, so we have a so-called simplest kinetic model that relates F, the fraction of conversion. We're going to refer to this concept a lot. The fraction of conversion, which means out of the matrix phase, what's the percentage, what's the fraction that got converted into the new phase, which we call precipitate, for precipitation type of phase transformation, relates that with time t, and of course with other factors that are part of our model, part of our assumption. And one note about this equation is that it only applies for, read to yourself, very low extent of conversion. Very low extent of conversion. When this f value is much smaller than 1. How small? Let's say it's 0.01 or 1%. Or 0.05 or 5%. Okay? Higher than that, then it becomes complex because the assumptions about constant nucleation rate or constant growth rate or no overlapping will not apply. Okay? That's what we said. This equation holds only for, read to yourself, very low conversion at the very beginning of the phase transformation process, when f is much smaller than 1, when f is very close to 0. Otherwise, you cannot assume constant nucleation rate because it's going to impact. You cannot assume constant growth rate, as you can imagine the precipitate may bump into each other and stop. The constant growth rate is no longer true. And also you are neglect overlapping case. Okay, if there's overlap, then it means new nucleation cannot happen, and it means this equation will not apply. Okay.